Okay, I want to continue to the second part. Okay. It's still spooling. Okay. Send request. Okay. Okay, so I hope everyone is recharged and refreshed. Also, those who are attending online, I hope you have had some chance to stretch and come back refreshed. So this is connected to two aspects. The first one, the one that we covered this morning about code base. About Shor algorithm. So the motivation is we want to look at alternative mathematical structures that will allow us to protect the crypto system from Shor algorithmic attack and other quantum attack in general. And this is also a continuation of Professor Putranto's lecture. He already covered the basics of linear codes. I believe he also showed you humming codes and so on. Perhaps I will start with another slide just to show you one slide. Here in my first lecture, I realized I didn't give you my contact email. This is my NTU account. This is my account in Sandiguna. So I'm not sure if everyone knows. In NTU, I'm actually only an adjunct professor. In that sense, I work part-time because the university asked me to continue teaching and continue doing research with NTU, actually with the same group that I graduated from many years ago. But my full-time job is with Sandiguna. In Sandiguna, I serve as the resident cryptographer and general helper. CEO is that, I think, someone that makes sure that every team has a support system that they need. So are the two separated? Not really, because Sandiguna does a lot of research also within NTU collaborations. And also, we have close collaboration between industry and academia in Singapore. Typically, I spend 80% of my time Sandiguna, and I spend 1 or 2 days full in NTU, either for teaching or for research. And for research, my focus is, of course, post-quantum cryptography, but also quantum error control system and trusted execution environment, a few other things. I have quite a number of interests. So in Sandiguna, we are building core cryptographic products. So we build key management system, we build cryptographic services in secure environment. Today, we're not going to discuss that directly, except that when people ask me, what is the implementation of all of this in real life, in industry, I can easily say, well, you look up our product profiles and then you will know that it's being used. Okay, so a few government agencies and a number of financial service institutes in Indonesia are already using our product. I cannot tell you which one. So I shouldn't be saying that. I mean, which one is using our product? But let me go to, yes, this one. And let me go to this. Sorry, I will go straight into. What happened? Why am I here? Here. Okay, so because of all this business with Shaw algorithm and Grover algorithm, right? Then we started, the cryptographic community started this post-quantum cryptography standardization process. How many of you here are familiar with how cryptographic modules become international standard? For encryption, we have AES, which is Advanced Encryption System. The original name is Reinder, not AES. When it becomes standard, it's renamed to be AES, okay? Advanced Encryption System. Now for SHA-2, the secure hash algorithm 2, it becomes a standard through process as well. SHA-3, the winner of SHA-3 competition, the original name was Keccak. Keccak, K-E-C-C-A-K, Keccak. So typically, when there is a need to create or to standardize a certain algorithm, this is usually done internationally, open. The algorithms are not protected by copyright. You can access the source code, you can replicate the implementation, and so on and so forth. Why are we doing this? Because in the olden time, every country have their own system, they build their own system, and that creates a lot of problems. Because nowadays, the internet covers everybody, right? Everybody all around the world are using the same protocol. So imagine if they use different non-standardized protocol, then it will be very, very messy. Second, when you build products like laptops, handphones, and so on and so forth, without standards, which algorithm to implement and everything, things will just be so there will be a lot of problem with interoperability and also a lot of problem with hardware. Everybody needs to make their own hardware. Okay, so for the purpose of international usage, standardized usage, then we have internationally accepted cryptographic modules. When we talk about banking, when we talk about financial services, there is a very strict standard. You must follow this, you must follow that, you must follow this, you must follow that. Okay, there is a standard for payment system, there is a standard for cards that can be used as credit card, debit card, and so on and so forth. There should actually be standard for our KTP, but I don't know if that's being followed rigorously or what kind of security is put into it. Probably very good one, because then you need to be able to say something about it when other countries or the international community is asking how secure is this system. So in cryptography, the module, the algorithms are all open, right? What do you keep secret? The keys. You protect the key, you manage the key, you keep your system safe. Why can we make the system open, the algorithm open? The answer is again, because there is mathematical guarantee to it. There is a mathematical guarantee to it. Opening up the system, putting it out in the open does not compromise security. Does not compromise security. So that's the magic of mathematics in cryptography. It enables the system to be open. The key, however, the keys are the one that you need to take care of. So when we started thinking seriously about all this quantum cryptanalysis of existing system, the international cryptographic community started talking, okay, so we need to be able to create or build crypto systems that runs on normal digital computer. All of the algorithms here do not require quantum computer. Again, do not require quantum computer. But the requirement is we must build crypto systems that are not vulnerable against all of this quantum attack. So that's the spirit. You see, the process started officially during Eurocrypt in 2016, when NIST is a federal, so the US standard body in Indonesia is maybe the SNI, Standard National Indonesia. So there it's NIST. It's under Department of Commerce. So they are not imposing any conditions on it. So the conditions, the requirement for the algorithm are decided by the international mathematics or cryptographic community. NIST organize it. So they put funding on it, they organize conferences, they do the administrative work and so on and so forth. So the decision on which algorithm to take and everything is weighted on by input from everybody who cares to join. So it's not NIST like imposing, okay, we use this one. Because the winners are actually not American. Many of the winners are not American. NIST is a US agency. So there NIST announced, okay, let's get starting to look into quantum, post-quantum algorithm. In November 2017, the submission. First round candidates, of course, when it's submitted, then the candidate that passed the initial screening is announced, and then a year and 2 months later, then you have the second round candidate. So what happened between the first round and the second round? Open season, attack. Those who can attack the algorithm publish the attack and show whether this is good or not. Or maybe they challenge the assumption of the designer. Are you sure you want to use this because this has limitation, this has weaknesses, this has this and that? Or they challenge the implementation. When you implement like that, it's actually not secure, and this is how I attack it. So that's what happened when the cryptographic community started, preparing for standard. So this is all, the process is open. The third round candidates. So between the first round and the second round and the third round, of course, many of these candidates are set aside. They're either shown to be not practical or not secure, or there is some problem with them. So they're kick out until in the end we have small number. July 2020, I'm actually very much involved in this. In fact, with a few colleagues in Singapore, we actually produced an attack on one of the finalists. And our attack is considered to be one of the reasons why that finalist is actually crossed out. So we did a complete key recovery. So we actually catched it. But that's a lot of work, actually, a year and a half. It's not easy. But that's how the international community is working on this. We really test the algorithm. We really test the module. We challenge all the assumptions. Okay, now July 2022, so about a year ago, the algorithms to be standardized are announced along with an alternate candidate advancing to the fourth round. So even after the third round, we are not satisfied with some of the result. Maybe we are not sure whether this is really secure. Maybe we have issue with implementations. Maybe we have some questions about whether this is supposed to be put inside or not. First, of course, security is a big criteria. Second is efficiency, because often not the most secure is chosen. Often what is chosen is the best combination of these two. Number three is whether the module, the cryptographic module, can be implemented on existing infrastructure. Because if we need to change the infrastructure, there will be a lot of resistance from industry, from people who are actually using it. So the question is, can we build an algorithm that withstand quantum attack, easy to use, efficient, and does not require a lot of new stuff to be built? So those are some of the considerations. And now let's take a look at what happened. So which one are to be standardized? For public key encryption, for KEM, this KEM is key encapsulation method. We have Crystal Kyber. This is lattice based. It's actually module learning with errors. This is ML module learning with error, LWE, MLWE. Crystal dilithium is the pair of this. Like RSA and RSA sign, they use similar structure. So, anyone here a fan of Star Wars? You know why the name Kyber and dilithium? Because the designer decide that they like Star Wars and they use this. Kyber is the sword in Star Wars. And Falcon, I think is based on lattice also. It's based on N-through. Sphinx is based on hash. Sphinx is based on hash. Now, if you look, right, digital signature, we have 3, but 2 of them uses a similar mathematical structure. And this one uses hash, this one uses lattice. Here, the public key encryption is only 1. We are not happy with that. Again, back to the question in the morning, what happened if this is actually vulnerable? 5 years down the line, we find it vulnerable. We don't have anything to back it up. Then this is dangerous. We should not let this happen. That's why the process continues. So here, at this stage, you can read that internal report. I will mention why it's updated. See what happened here? We need to fill up something here. We need to put something here. Oh. Okay, and here you look by classic mechanism and Hamming quasi-cyclic. Tomorrow's lecture by Prof. Lingsan is about quasi-cyclic. There. And Hamming is the metric being used. It was explained by Professor Putranto. Hamming is just you look at the difference of the entries in every position. That's a Hamming distance. There are other things like the lead distance. There are other metric, okay? Usually for radar system, they don't use the Hamming metric. Now, site is isogenes. This announcement is July, right? August, this is broken. And it's completely broken on a laptop over an 8-hour period. So if the attacker has dedicated server system, it probably takes seconds. Because if you use laptop, it takes 8 hours. If you use powerful computer, it's probably done. Now, this is very surprising because the mathematics and the geometry and the algebra here is very advanced. It's isogenes, and people think that, wow, this is awesome. Nice, right? But this is broken. And then they try to fix this, okay, it's broken, try to fix it. It's broken again, and it's broken again, it's broken again. So then we just say, okay, so we shouldn't touch this anymore. We just cross it out. Okay, so this is completely broken. It's a complete key recovery. When it's complete key recovery, there's nothing you can do. Nothing you can do. So we cross this out. That's why it's updated September. Because here it's still going into that. So to put the context, what I'm going to discuss, I'm going to try to guide you through is this. The classic mechanism. This is 1 year older than me, this crypto system. So you see, from security perspective, this is very trusted. Very, very trusted. More than 40 years of no devastating attack. Okay? So that's where I'm going to put the context. Okay. Now, what happened to the digital signature? Why is this empty? We have 3 and 2 of the same system. But the question is, where is the code base? There is no code base here. There is no code base here, getting into that. So it's actually not empty. This creates an entire new cycle for digital signature. Because digital signature nowadays, if you look at it, sometimes we want, now people talk a lot about IoT devices, right? These are fantastic devices, right? What is the problem with these fantastic devices? They are light. They don't have much computing power. But they have now become more and more essential part of critical infrastructure. PLN, for example, the Indonesian state company for electricity, started talking about smart meter to replace all of this system of metering. And they started talking about IoT. So when they started discussing with us, our question to them is, that's part of your critical system. How do you protect the data? Because this is small system, right? And it's usually put outside. So attacker has physical access to it. It's not like you put a strong server at the back end of your banking system in a secure database somewhere that people coming in, have you entered one of those secure databases? No? There is a biometric. You know, you need to show biometric before you can go in. Second, when you step in, there is a scale. Ada timbangan. There is a scale, you need to step in, they measure what's your weight, and then when you go out, your weight should not be more than that as well. Okay? Now, if you have been inside some of the secure data center, that's the protocol. I cannot wear this, no belt, shoes off. I go in, they wait. Then when I go out, they wait again. There is a lock system, who goes in, when, why. But these IoT devices are out in the open. Now, if I'm a malicious agent, I can attack an entire electrical distribution system by spooking one of those devices. Or I bring my own device, put it in the system, and bypass the security there, and I do injection attack. So that's very dangerous. Now, for signature, we need a lot of variants. Variants that can go into IoT, variants that can go into very secure system, variants that are implementable in different environments. So what's the good news then for us? A lot of research problems here. And I'll give you research problems. Some of you ask, what should I do for my thesis and everything, right? I'm going to give you problems. I like giving problems. Solution I cannot find. I cannot find solution. You see, when they say that mathematics are young people's game, then maybe they ask me, as a researcher, you're not as productive as 5 years ago. Yeah, I'm older. I just say the next generation, you ask them. Ask the next generation. So this one just came out a few days ago. The digital signature scheme, I told you that's a new cycle altogether, right? Today, what I'm going to discuss for you is the McAleese. Now, this is a summer school, right? It's a research school, right? So I'm giving you research problems. I'm not going to solve for you. I'm done with PhD long time ago. Don't need that anymore. So you see here, code-based signature. There is a Korean team here. And this is, I know Antonia in person. I know Violetta as well. So these are French. This is in Swiss and Germany teams. Okay. And Marco, I also know. So many of these are friends. Of course, you know, the community is quite small. So here you see, you said you want to go into code-based crypto system, but you don't have open problems. I give you open problems a lot. So here, you see this new proposal, just passed the first round. Attack them. Find weaknesses or improve them. You say, this part of the algorithm, I can make it faster. Then do so. That's open problem. Good enough for your master's and for your PhD and maybe for your postdoc. So that's secure your career. If you want to go into academia, you know, you apply for funding. This is a hot topic. Those with money to give you for research may not understand this, but you can sell it. This is post-quantum, you know. So you see? Now, if you want to see what is inside here, well, go to the specifications and learn it. Okay, some of you might be saying, I'm not a hardcore mathematician, I'm more of a computer scientist. Good, 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 good. You cannot run away. There is a source code here. Read the source code. Understand it. Okay, so this is taking long. But anyway, if you go through that, I think this one is quasi-cyclic using a Lie matrix. This one is, that RM there is Rittmuller. It's a Rittmuller code. Rittmuller code is usually not used for post-quantum, at least as much as I know, because Rittmuller has too much structure. And I know the difficulty of making signature scheme in cryptography, because many years ago I was working with your advisor, my colleague from Korea, Hyung Tae Lee. We tried making code-based signature scheme, and after 1.5 years we tried, we didn't find anything, we gave up. So you see, sometimes you look at researchers and then you look at their publication and you say that, whoa, this one published there, wow, this one is in that journal. What you see is the one that got published. You don't see the one which are rejected. A lot more. So when I meet young researcher just starting, they come to me and say, sir, my paper got rejected, the referee is very mean and stuff, and I was just laughing. If you cannot stomach it, this is not for you. If you cannot handle rejection, don't be a researcher. Rejection is part of how we advance in research. Okay, not necessarily that rejection is correct, but in my experience, if your work is good, it will be appreciated at the end, wherever it gets published or whoever you're discussing it with. So if you have a crappy results, get accepted in high journal, don't be too happy. Somebody a few years later can write something to that journal and saying, this is wrong, this is not important. So you see this? In front, there is a preliminary after the signature saying that we are not keeping copyright, blah, 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 blah. Okay. Then it says here, overview of the basic idea. You see that? Lie matrix, Gilbert-Farshimov bound, bang. A lot of fun stuff here. You said there is no open problem? Come on, open problem a lot. A lot of open problems, okay? Have fun. So any questions about the background? Spend quite some time on the background. I think it's very important to position it. Any questions? A lot of interesting problem, don't worry. And a lot more. Okay, so let's go into this GOPA. It's not very difficult. All right, so I'm just going to review quickly what is the general scheme for it, right? So megalist hides the structure of the generator matrix. Meter writer hides the structure of the parity check matrix. You know that the two are closely connected, right? One is a generator matrix, it provides you the basis for the code. Now, the parity check matrix is the null space of that code, right? It's the null space. So essentially, if you have a code C, you multiply it with the transpose of the parity check matrix, it should be 0. That's a null space. But of course, the dual of the code is generated by the parity check matrix. And if you use inner product, like the Euclidean inner product or the Hermitian inner product, these inner products are non-degenerate. So you know the dimensions, you know how to deal with them, and everything is crystal clear. So if you ask me, why do we learn linear algebra? I would say so that you understand mechanistic cryptosystem. This is simple linear algebra. First course, nothing more than that. Okay, just matrices, linear combinations, all these things, okay? You're looking at linear transformations, also matrices. We're not talking about eigenvalues, eigenvectors, eigen whatever. Nothing like that, just pure basic linear algebra. Okay, so now the original framework is already described. I believe Professor Putanto also discussed. Now, what happened is you have a generator matrix of some code. Now, this generator matrix, you multiply from the left by some sparse invertible matrix, and from the right by some permutation matrix. What does this permutation matrix do? What does it do? It actually scrambles the positions. Okay, it scrambles the positions. And that invertible matrix from the left that you do is to confuse your adversary. Because when you multiply it, you change the combinations. And then you put some error. You put some error. The error here must be bounded so that your original code can decode the error, can clean up the error afterward, right? You still remember this? I start seeing some blank faces. Okay, you don't recall it? I can go back a little bit. As I said, we don't have to finish the material. More important thing is everybody sort of still hanging on. Okay, so now the encryption is very simple. You have a message, G, you treat it like a vector, and then you multiply it with the generator, the public key, which is this one is a DG P. P is permutation matrix, D is an invertible sparse matrix, and G is the generator of your COPA code. Okay, so this is how you encrypt, and the decryption is easy. First, you remove the error. After that, you perform the decoding algorithm. After that, you get the original message. Now, I'm going to switch your point of view into a bit of geometric point of view, right? We're talking about space, vector space, subspace. So it's a geometric problem, right? Now, I want you to close your eyes. All of you, close your eyes. Close your eyes. Now, imagine you are in this room. And in this room, there are some points. Or if you want balloons, there are balloons in this room, and you arrange the balloon nicely. You arrange the balloon nicely in a row, okay? So there is some symmetry to it. And then you change the dimension, you change the basis. You change the basis of the room, and now everything becomes weird. And then now you add error. Adding error means you are shifting some of the balloon a little bit, not all, some of the balloon a little bit in different directions. So that's how the room looks from the attacker point of view. Okay, as messy as you imagine in your mind. So how can you recover from that mess? You know the error, so you can correct the error. You know the original basis. From one basis to another basis, you do invertible linear transformation, right? To go back, you apply the inverse of the transformation, then you go back. You go back to the good basis, and then you get the message. So this is the algebraic explanations. Now you can open your eyes. This is the algebraic explanation. That's how I imagine it. I have a space. I put regular object in the space. Okay, they have the same distance to one another, regular distance. And now I'm messing it up. I change the order, I change the basis, and I put errors. That's how it looks like from your adversary. And remember, the number of basis choices grow exponentially as your dimension grow, right? There is a formula for that. The number of possible bases. All right, so that's how all of this business of code-based cryptography. Very simple. Now, I want to go back into Shor algorithm. Why is Shor algorithm not working against this kind of structure? Why is it not working? The key step in the quantum part of Shor algorithm is period finding. Here, you don't have any period to find. Because the error make it not periodic, the change of basis make it really screwed up. So that's the mathematical thinking behind it, the philosophy behind it. The technical aspect, then you can start work on the algebra or the geometry. At least you get some idea on what's going on there, right? After all, this is a research school. We talk about idea first. Then the technical details, you fill it up. So, an interesting question would be to find a hiding trapdoor with a proven indistinguishability. What are these people saying? The backdoor is when I give you the public matrix, the public generator matrix G prime. G prime is D, G, P. P is the permutation. D is just a matrix that you add to scramble everything and to make it really messy. Now, the question is, how do you choose your G, your D, and your P in such a way that it's really indistinguishable from randomly generated matrix? This G prime, this G prime must look like a random matrix, must look like a random matrix to your adversary. That's why a very strong structure like cyclic code cannot be used. A very structured codes like Ritmuller cannot be used directly. Professor Putranto show you humming code. That is too structured. You look at it, it's not random. It is very, very structured. So the main question here, the philosophical questions that underline the entire security of this system is the following. Can you choose a family of code that you can make look very random? Look random to your adversary, but to you it's not. That's the key. To you, it is not. Why? Because if you choose randomly, how do you decode? You need the decoder which is fast. The decoder that is fast rely on structure. If you take a random code, fine. It's a random code. It has nice property. Yeah, okay. How do you encode that in circuit? How do you decode that in circuit? Don't know. That's why the challenge here is not just to pick any linear subspace. Picking any linear subspace, you can just toss a coin. Okay, I take this vector, I normalize, take another vector, normalize, I take another vector, right? The Gram-Schmidt, you do that as an undergraduate. Very simple, right? No, can you build a crypto system like that? Yes, you can. Perfectly. The problem is how do you implement it? If every time you want to encrypt, you build something randomly, then you what? You make a random computer, a random gate? No, it cannot be. It should be a structure which is for you very clear. It has efficient encoding and decoding algorithm. But to your adversary, it should look random. Okay, so I hope this is clear. Question? So we have this VCH code, Jose, Chowdhury, and Hockenheim. We've tried it. It's not secure. What about humming quasi-cyclic? Well, there are some attacks that work. There are some attacks that can be mitigated. So the situation is we're not very clear about it. It depends on how you choose your D matrix. Sometimes it depends on how you build your quasi-cyclic. So the situation here is not very clear. If you refer to my slide earlier, HQC is still part of round 4. Okay, so Prof. Insan will explain quasi-cyclic tomorrow. Now, rank quasi-cyclic is different. Right now, the rank matrix says I represent my vector, my code word, as matrix. And now one code word with another code word, you measure the distance of them as matrix. How? The matrix has rank. So the code word A has rank N, code word B has rank M. The difference is the rank difference, is the rank metric. So at the beginning, there's a lot of excitement about this rank metric because it seems like it might be working, but then there was an attack on it. So it's basically not secure. What is still secure? The original McAleese, and the code is a binary Copa code. If it is not binary, if it is over extension field or over F5 or over F7, what happened? It's actually not secure. There's a proof for it. There's an attack. Not too long after the writer issued released the paper. Okay, I forgot the name, but it's too Russian. I forgot the name, but they showed how to attack if it is not binary. If you ask me why, I can explain to you the technical aspect, but the easy design philosophical explanation is when it is non-binary, actually it reveals more structure and it doesn't seem random to the attacker. So when it's binary, it's actually the randomness is actually good. And if you ask why is that so, I would say, I don't know. I don't know. Because intuitively, you will be thinking, well, why binary? Why not over F4? Why not over F8? Why not over F1 to 8? It's an extension that we know well, right? In mathematics, in finite field, it's something easy, but it was shown that it's not secure. Now, the part I highlight here with calibrated parameters, what do I mean with that? With calibrated parameters, I mean the original McAleese is old. As I said, 1 year older than me. So when it was proposed, they used what is secure with respect to the computing power available then. Right now, the computing power is much higher. So that original parameters is no longer secure, but the system overall is still secure. So what happened? Well, you choose a code with much longer length and much higher dimension. It's like RSA. If I ask you, is RSA secure? Your questions can be answered depending on who your adversary are and how long your key. If somebody say, yeah, RSA is still secure, I would say, okay, I use P equal to 5 and Q equal to 7. That's of course not secure, right? Now, even if you use key length 1024, it is considered no longer secure. So 2048 is for general public, but if you are a root CA, a root certificate of authority, usually you use RSA 4096. You don't use the small one. So the original parameter is no longer secure, but it's not because the system overall is insecure, but because that parameter is now within the striking reach of existing computing power. I don't want to reveal my age too much, but when my first laptop, I bought it when I was already an undergrad student. It's very thick and very heavy. And nowadays, thinner, lighter, but exponentially more powerful, right? So the original needs calibration, but it's still safe. So who proposed this COPA code? Of course, COPA in 1970s. Gopa insight is the following. One can construct codes with excellent properties from algebraic curve by using rational functions and differential forms on algebraic curve over finite field. So first, you pick up a finite field, and then you create an algebraic curve. There is a requirement for this algebraic curve. For example, it must be this, it must be that. But for our discussion today, let's assume we have chosen a good curve. With good, I will not define, but it's good. It's a good curve. Then I pick up points on there. I pick up points, and then I create this set of rational functions. Set of rational function is like functions, but it's rational function. So it's a function over a function. Okay? It's an f something over g something. Fz over gz. And of course, when you see over, you need to be careful with the z where gz equals 0, because that will create trouble for your equation, right? Now you choose this set of functions, and then now you use this set of functions to evaluate those points. Those points you evaluate on those rational functions, it gives you vector. You use that as your code words. Okay? So then, not too long, this TVZ, Schaffman, Vladu, and Zing, some algebraic geometric codes are better than random codes, better in terms of performance. They're consistently performing well. So performance, when you talk about coding theory, right? Performance, what is performance in coding theory? Remember, coding theory was not designed to hide messages. In cryptography, we hide something so that other people cannot see, but we open it to people with credential to look at it, right? Coding theory is different. Coding theory's purpose is to make sure that we can control error. So coding theory is about fidelity. It's about being true to the original message as much as possible, given errors in the channel. Now, cryptography is different. In cryptography, you want to hide things. You want to cover and uncover. Okay? Now, when I say performance here, in the coding context means they can handle error better. Okay, they are more energy efficient. So not performance better in terms of cryptography. In cryptography, what we need is they look random. That one is what we need. They look random, although they are full of structures, but they look random. Okay, so the study of geometric objects. So when we go into this algebraic geometric code, so Gopa code is an example of a family of algebraic geometric codes. In algebraic geometry code, you start with some finite field, you pick up a curve, a good curve, you choose points on that curve, and you define a set of functions, a space of functions, and then you evaluate those points on that space of functions. You're all confused, right? I know. It took me 1.5 semesters to even understand the introduction. So, but you know, those are the main steps. And I'm still using algebraic geometry codes for research, as in really using it. So recently we have, from our group, we have 2 papers accepted for a conference in September in France. And we built new class of quantum codes using algebraic geometry. So it's still very much alive, still very much used. So in most coding theory application, the geometric objects are curves and point of them. The codes are evaluation code. As I mentioned, you create a space of functions, then you evaluate these functions on those points to get you the code words. Okay. The entries are evaluations of functions on the chosen points in the specific curve. Okay. There are 3 common roads in studying AG codes. The first one is the one that happened to me, and I think that's very painful. I start learning about algebraic function fields. So this is like very, very technical, very abstract. And then later on, when I'm already a researcher, I start looking at it from a more geometric perspective. More combinatoric perspective. So I'm using association schemes. And then here, the second option is very algebraic. It's varieties over algebraically closed fields. So I'm not trying to dissuade you or make you scared. I'm just telling you this is what it is, right? If you want to learn all this algebraic geometry, and they have a lot of application in cryptography, there is a monograph by Professor Xing Xiaoping, Ling San, and Wang Wakshong. These are all my colleagues and previously my teachers in NTU, and it's specifically algebraic curve in cryptography. So everything there. So it's used in secret sharing scheme. It's used in a lot of stuff. Okay, but yeah, it's a bit painful to learn at the beginning. But if you have strong algebra background or strong combinatorial background and determined enough to go, it's useful. It's very useful too.
I have a question, sir. So can we put the material into undergraduate students?
It's a bit tricky. It's a bit tricky. But Ringson and Xing Xiaoping's textbook, Coding Theory, an Introduction, it has a chapter on Kobaku, if I remember correctly. But I think it's chapter 11 toward the end, or chapter 9. Okay, so have I tried teaching this at an undergrad level? No, I have never tried. But at least they tried in the US long time ago. Not in the first course, but in the second course. So I don't know how tricky it is in UGM. I think for the first course, sometimes there are not enough people who are interested, right? And much more for the second course. But I think the problem is often motivation. Because if you have to go into something which is very abstract, difficult, and let's admit it, painful, you need enough motivations. Because if you're not motivated enough, you keep asking, why should I be here? What am I doing here? Why am I even bothering with all of this? Right? Now, isn't that the problem we all as students experience? And of course, when I started doing research seriously at the level that I'm happy with, then I started knowing that, hey, these things that I learned very painfully before is now very useful, you know? I can just, that one. I think there was a result there in that textbook. I can just plug in, I use. Or there's a paper by Flooded and Zing from 1991. Oh, that one, I can use that theorem. That when you are motivated enough, but the problem is, for many of us, when we become teachers, when we become professors ourselves, we don't find it in us a way to communicate this to our students. That's another challenge. I'm not blaming my professor for not explaining it to me before because when I'm already in their shoes, right? When I'm already teaching, I find it, how do I explain this? How do I explain algebraic geometry to those who are still struggling about the concept of modules? So I'd say the challenge comes both ways. So you need to have students who are determined enough, and as teacher or as mentor, we need to sufficiently have a communication skill enough to explain that, look, yes, indeed, this is painful, but at the end, you will use this for something. And it's not immediate. That's the problem, no? So I'll stop at that. Okay, so these are usually the routes. Are there textbooks that you can use for this? Yes, many textbooks on that. But the background, the student should at least have done finite field, at least. Because as I said, right, the starting point is, sorry, where is that? Oh, yeah. You start with this. And then you define polynomials over that. The curve is defined as polynomial, and the rational functions are solutions to that equations. An example of this, many of us may be more familiar with, rather than COPA, is elliptic curve. Elliptic curve is an algebraic curve, it's genus 1. It's used a lot in cryptography, right? It's part of undergraduate education because it's easy to explain. The equation is y squared equal to x cubed plus ax plus c. Right? It's a lot easier to explain. But here in COPA is a bit is a bit more than that. So again, I'm going to skip a lot of introduction. I'm going straight here. Okay, we start with the finite field FQM for a prime power Q and some fixed M. Again, directly, you have an M degree extension of an FQ. I assume you know how to do that. Okay, now you build a polynomial ring in indeterminate Z. So here's a polynomial ring. You look at the coefficients are from the field. And this is general. Okay, now you choose a polynomial G in the ring, and now you let this condition be satisfied. So you choose finite fields elements, okay, into a set, you choose a subset of that FQM, and now the subset must not intersect the zeros of GZ. This GZ has zeros, right? GZ has zeros. Then now you want to choose components which do not intersect with the zeros. I think some of you started to see why this must be. Because if this is included in the zero, we have a problem. When we evaluate, it goes to zero. You cannot divide by zero. Okay? Now, you look at the vector here. Be careful. This is FQ. That is FQM. This is FQ. Okay? Be careful. Now here, if you choose this vector, then these equations define what? A polynomial. This is a polynomial. Look, the Z is indeterminate. The Ci come from here, alpha I come from there. So this one comes from the extension field. Then you can look at this is actually as a creature in FQM Z. It's here. It's in that ring. That's why it's important to have this. Otherwise, you have a problem. You have a problem here. Okay? Sufficiently confused? Good. Let's go. Now, what is the COPA code? The COPA code is now evaluation. Evaluation by what? By what? That one polynomial. So the COPA code is an evaluation depending on L and G. So you must define G first. You know what are the zeros. And then you say, I'm taking a subset of FQM containing points which are not in the zero. Now I need to get that, and then I define this. The elements in this code, the code words there are the zeros here, modulo G. The zeros modulo G. So that's how you define a COPA polynomial. How is that choice come to be? You ask Valerie COPA. I don't know. I think it's because this is simple. Look at this. It's just a sum of simple fractions. Right? It goes from I to N. So you use all of this element in L. And that's what you do. It's a fraction plus a fraction plus a fraction plus a fraction. There's a polynomial here. And what are the zeros? The alphas. You want to avoid that. You want to avoid that. Because if alpha is not in the zero of this, then this is non-zero. Right? So that means it's well defined. Because if there is an intersection here, you may have a something over zero, and your entire system is not well defined. It blew up. That's why we have that. Now, the COPA polynomial is that GZ. GZ is that COPA polynomial. Okay, there are a large number of such G. Why? Look at G. Okay, look at G. Choose a polynomial G in the ring. Look, for every element here, how many choices do we have? Q to the M. So you have Q to the M N. That's huge. That is the source of randomness. It should look to your adversary random because picking up the right GZ, picking up the right Kopa polynomial is already very difficult. You choose something at random from this big set, okay? So the cryptographic key space is large because the key space comes from the Kopa set, okay? Now, when GZ is irreducible, irreducible means, well, it's already in the lowest form. You cannot calibrate you cannot divide it with something else, okay? Then, rather than the trivial one, of course, then this code is an irreducible Kopa code. So essentially, you must choose G to be irreducible. Typically, that means this one is 1. This is 1. Then you just must choose that this cannot be factored into smaller one. Okay, it cannot be factored into smaller one. And how to generate a irreducible polynomial in this space? There are known methods to do that from the study of finite fields. That red book by Liddell and Niederreiter, I think in chapter 2 or 3, I can't remember now, there are ways of doing that. Okay, so is this code well defined? Okay, somebody asks you, what is the purpose of learning abstract algebra? This now you know. I'm sure you have heard about unique factorization domain, right? Yes. What happens if it is not uniquely factorized? Well, it's not well defined. But here we deal with unique factorization domain, so fine. And again, in fact, here we use modified Euclidean algorithm, right? Right? Yeah, and in Chinese remainder theorem and all that. Okay, so related to equation 1, where is equation 1? This. You look at it, notice that this product is actually 1 modulo G. Okay, that I can just expand. You can do the computation later. I think this is correct. I did it 2 or 3 times. I checked. You have that. It's just a simple arithmetic. You have this. Now, that is a polynomial in modulo GZ. So we can write this. You remember this? This is the summand in that equation 1. Equation 1 has that summand. I can write it this way. Therefore, this congruence in the definitions of the code means GZ divides this expression. And this is important again, that reason why L should not contain any roots of GZ, because if L contains any root of GZ, then here we don't have this nice congruence. Now, GZ minus G alpha I, this G alpha I is actually a specific element in the extension field, right? It's a polynomial of degree T, GZ has degree T. This is clear. GZ is degree T, this is a linear one. Okay. Now, C, a vector C is a code word if and only if this condition is satisfied. What does this tell you? This tells you we can easily consider this like the analog of parity check matrix, right? Parity check matrix, a code word is inside the code if C times the parity check transpose is 0. Here it is. This is how you check it. So this is a polynomial check. It's not a matrix parity check, but it's a polynomial check. So C is now written as a polynomial. Okay? Now, Kopa codes are linear. Well, homework, closure under addition, and scalar multiplications. So it's a subspace, it's a space. It's a vector space. Okay. Now, let's go into something more familiar. I know when you look at all these polynomials, you go like, huh? What are those things? Of course, you are too polite to say it, but you're saying that, what? How do we get there? Okay. Now, I give you a Copa polynomial of degree t. I give you L. And then as we have just analyzed in a few slides before, this code is a well-defined code. That's a Copa code defined on L and G. Okay. Now, I can express, based on these results here, this is a check polynomial. I can express it in a more familiar way. You see? Algebraic geometry goes so high up there in the algebraic abstractions, and then in the end, oh, okay, it's just that. You go back down, you look at the evaluation. Look, this is just an element. It's alpha 1 evaluated at G, and then you look at the inverse. Remember, this is an element of finite field, they have inverse. And the choice of alpha 1 not in the root means this is non-zero. Okay? So it's consistent. It's non-zero, so here you have a well-defined expression. Now there you are. This is how Copa code is expressed in real parity check matrix. And here, you know the parameters. The dimension is at least n minus mt, and the distance is at least t plus 1. This one comes from a very famous theorem called the Riemann-Roch theorem. Riemann, you know, Roch is another person, R-O-C-H. It's a Riemann-Roch theorem. Okay. Now here is a generic example. Okay, so the generic example, let's cube it to Gz is simple, just z. So what is the root of this polynomial? 0. So your L must not contain 0. Okay? So now I throw away the 0. So L is just everything else but the 0. Simple. Now, I can then define Copa code. The parity check matrix is just this. Looks familiar? Looks familiar? It's actually Ritz-Solomon type. Okay, maybe you're not familiar with Ritz-Solomon. Sorry. But look at this. What are these? You pick an alpha, and this is just this one. Just a power of alpha. And you know that they are linearly independent, right? Right? So this code is nice because the distance will be high. Okay? So then you can derive actually a narrow sense PCH code. So Copa code is a generalization of cyclic code. A much generalization of cyclic code. And PCH is a particular case of cyclic code. So yeah, so any valid Q and M, let alpha be a primitive. So I give you two examples. The first example is just super simple. This is actually a Ritz-Solomon code, which is maximum distance separable. Was maximum distance separation discussed in Professor Putranto's lecture? Maximum distance separation? No? Okay, never mind on that then. So the second example, I choose any valid Q and M, and now alpha is a specific. It's a primitive element of FQM. So now for my Copa polynomial, I choose z raised to t, and L is this. Because it's a primitive element, you know that this is also actually well defined. Okay, so instead of the alpha power 1, you now look at the inverse. Okay. The line is q to the m minus 1. Now, the parity check matrix you can easily find. And this is very nice matrix. the linear independence and everything is super nice. But again, I'm not talking here about the niceness as codes, because in cryptography, that niceness as code is sometimes not really important. Okay. I explained before, in coding theory, we want to make sure that we can correct error. So the optimization is usually on the error correcting capability. In cryptography, we want the optimization in terms of random lookingness and the speed of encoding and decoding. Okay, Copa code has a very nice decoding. Why? You look at the parity check matrix, it's super nice. The parity check matrix is used to find the syndrome. The syndrome is used for the syndrome decoding. So in fact, looking at the form itself, the generic form, you look at the generic form here. What matters is your G, your Copa polynomial, and your choices of the alphas. Your choices of the alphas. And that's it. So it's very nice. Now it's more explicit, small example. So let's kill this 2. Alpha is a primitive element of F8, satisfying this. So if you look at it, our extension polynomial from F2 is actually x cubed plus x plus 1. Okay, I see some blank faces. How many of you have not taken finite field? Not taken finite field? Not yet. Okay. Who else? Not taken finite field? Everybody has taken finite field? How do you build finite field? Here you choose an irreducible polynomial in Fpx of degree m. And here you have this, you can express this as Fp alpha, where alpha is the root of polynomial p. Sorry, no. Here, x, root of here x. Or you can express this as set of polynomials. Okay, so voila. If you're going back here, that's how you extend to F8. So from F2, you extend to F8, and your polynomial here is x cubed plus x plus 1. Okay, so this irreducible here you use is x cubed plus x plus 1. You can verify that it is irreducible. I think it's even because it's primitive element. I think that's what do you call it? It's a primitive polynomial. Okay, so it's governed by this. Now we take as our Copa polynomial this expression. Look, it's different from here, okay? It's different from this polynomial. It's not that polynomial. Why? We want to avoid the 0 meeting the choices of F. Okay? So L is F8. And this, you need a certain relation so that you don't have that clash on the choice of L. Okay? So N is 8, so the length is 8, and M is 3, so we know the dimensions, okay? So here's the parity check. So at the beginning, you see Copa code, it looks very, very abstract and stuff, but it's actually when you choose the polynomial, when you start doing computations, they look much better. Not as scary as the abstraction look. So here's usually my advice and also what I'm doing. When I'm confused about very abstract mathematical structure, I will just start choosing some toy example. And start looking at if I multiply with that, what happened? What is the Hamming distance between this vector and another vector? So really get your hands dirty pick up a piece of paper, start writing down there. Then at least you get a sense, oh, that's what that abstraction means here. So here's an existent theorem. So there is a QRE Gopa code where GZ is an irreducible polynomial in that ring FQMZ of degree T, and L is actually in the entire FQM. And that's the parameter. Q to the M is the length. K, D with K is bounded low, so it's bounded below. So it's at least Q to the M minus MT, provided that you have this inequality. So what is the importance of this theorem? There is. We are guaranteed that there is. There is. And the choice for Megalis and Niederreiter crypto system Q is 2. So there is a binary Gopa code where GZ is an irreducible polynomial in FQM Z of degree T. We don't really care about T, but M is large. Okay? So when M is large, what happened? Your length is large. Even if this is 2, M is big, that's large. And remember, K is bounded below by this expression. When M grows bigger, what happens? This becomes dominant, this becomes dominating. So when M is bigger, what happens? Your dimension is actually almost your length. You see? When M is big, this one grows faster than this, right? Your length is Q to the M. Your dimension, as M grows bigger, is almost that. So the rate of this code, the number of information it can carry, is high. Now I'll say something about this. That's why I highlight, because this is important. Okay? So remember this. We'll get to this later, very soon. Now, what about D? For cryptography, the error correction capability doesn't really matter that much. Not as much as for coding theory. In fact, the original Gopa is simply saying, well, if you can correct about 50 error, I'm happy for a very long length. Okay? So imagine if you have 50 error, that means you change some values in 50 positions. That's already very, very confusing for your adversary, because your playground is already large, right? What is your playground here? Binary. So if you have the number of error is up to 50, so that's 2 raised to 50. That's a lot to find. Just on the number of error already. Okay. So okay, I already moved. It's not yet there. It's frozen here. Okay, I'm resharing. I'm actually locked out. It's okay, we are not, we're just about 3 slides away from the end. Yeah. Let me log in again. Okay, while we wait for this, the message here is that Gopa code looks really random to an adversary. it has structures which are, it has structures with, because of your arbitrary choice of the GZ, right? Because your arbitrary choices of GZ. And then the freedom to choose L. Remember, L is simply, you collect elements which are not in the roots of GZ. So you have a lot of choices. So given that, it is very difficult for the adversary to guess what is your COPA polynomial and what are your evaluation points. That's already very hard for the adversary. But for you who are the designer, you know what the COPA polynomial is. It's very easy because you can build the parity check matrix quickly. And if you know the parity check matrix, then your decoding algorithm can be run quickly. And if you know the parity check matrix, of course, you know the generator matrix. It's very easy to find the generator matrix from the parity check matrix and the other way around. Okay. Oh, I cannot screen share. I cannot screen share. Okay, so that's all right. Okay. All right, thanks. Okay, we are back. All right, so we are there. Now, what about the security analysis? Okay. Forget the first part here. That will bring us too far into complexity theory. But the structural attack on the mechanism, the main security assumption is the indistinguishability of the public matrix from random code. Okay, so the attack here is you try to recover directly G from the public key SGP. Oh, I use S here. No, I use D. This textbook use D, S. But D or S here is just a sparse random matrix in particles. Okay, so let's look at the instantiations. 1978, Macauley's proposal start with, we use binary COPA. The length is 1024. The dimension is about half. The dimension is about half of it. And W is D minus 1 over 2. So W is the number of error that this can correct. 50 is enough. So the minimum distance is at least 101. That's 50 times 2 plus 1. Okay, so if you look at it as a code, this is actually a code which is n equal to 1024, k is 524, and d is at least 101. Okay, now every time you instantiate, the COPA code is instantiated in the key generation phase. As part of the algorithm in the system, if you implement Macaulay crypto systems, in the key generations, the COPA polynomial is generated randomly. And then L is generated randomly. Although they're generated randomly, you know how to build the parity check matrix quickly, right? The parity check matrix is just an evaluation of G of over alpha something, or you take the inverse. Okay. There. The parity check matrix is easy to build. Once you choose G and you choose M. Okay, so that's the instantiations. All right. So now what happened? What is the biggest problem with Macaulay's crypto system? This. The size of this. The size of this. Let's look at the original COPA. matrix, this generator matrix is 524 times 1024. Yes? You store this type of matrix. Good luck. What about this? This one is actually 524 times 524. But maybe because it's sparse, you can only store some identifications on where it has ones or non-zeros and forget everything else. So maybe you don't store this much, maybe. Okay? Now what about this? This is a permutation matrix. A permutation matrix on 1024. So you can actually just store where in this permutation matrix, you can store this as a transposition, right? You can store this as some sigma transposition. So this is not expensive. This is only about 1024. So this is original mechanism, you see? Now, if I move this to 2048, and this to be something like close to 2048, what happened? More good luck to you. So, Bapak code is nice. Macalise cryptography is nice from perspective of security. It satisfies the analysis very nicely, okay? It's secure. Problem is, key size is that big. Okay? Now, you might be asking, so why use Kopa? Why not just use cyclic code? If you use cyclic code, the generator, you just need to store the first row, right? The next row is just a shift of it. But that's too easy to take, right? Because cyclic code, we know everything about cyclic code except the distance. Right? Cyclic code, we know everything about cyclic code except the distance. The distance is not important in cryptography. It's important in coding theory. So if you look at papers in coding theory, there's a lot of analysis on the distance, bound for the distance, blah, 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 blah. So many. In cryptography, don't care. Not important. But it's important that the structure looks random. Cyclic cannot. So now what about quasi-cyclic? Quasi-cyclic. Generator of quasi-cyclic looks like, well, here it is. Here it is. I can break it down into chunks. And here there is a cyclicity here, there is a cyclicity here, there is a cyclicity here. Okay? No more battery. Okay, good. So here we get into problem in code-based cryptography. Okay? If we use a code that looks random like Kopa code, our security goes up. Usability goes down. If we use a structure which is very nice for efficiency and key size, security just drops. Usability goes up. This is bad. We want something which is good for both. Maybe not optimal, but good for both. So that's where the problem with code-based cryptography. That's why it goes into the fourth round, the mechanism. Because in terms of security, everybody is happy. In terms of key size, nobody is happy. I shouldn't say nobody. There are some specialized agency with a lot of resources that don't care about key size. You know what type of agencies those are. Okay? But for public usage, for common usage, we care about key sizes. Because you don't want the memory of your phone to fill up quickly. And if you transfer the key, you don't want the key to occupy too much space. Your internet load and package will deteriorate quickly. Now, meter writer is pretty much similar to Macalise. It's just that instead of using the generator polynomial, it uses the parity check matrix. But parity check matrix is also generator polynomial, right? Of the dual code. So everything works pretty much the same. You might be asking, why are we looking at parity check matrix? I'll explain. When K over N is large, is almost N, then the generator matrix is big, but the parity check matrix is slim. Because you look at the dual, right? So it's N minus K over N. So here, when K is large, N minus K is small. So that's the reason why. So storage will be better. Okay, operationally it might be better. So that's the one of the main reasons. So I've explained to you what Bapak codes contribute into code-based cryptography, and this is my last slide. The original parameters are no longer safe, but this is due to advances in available computing power, not due to systemic problem. Okay. There is a powerful distinguisher attack on Bapak code with high rate, K over N at least 0.87. What does this mean? I mentioned to you that the Bapak code must look random, right? And the rate, as M goes higher, the rate comes nearer to the length. The length, if you remember, is Q to the M. The K, the dimension is Q to the M minus Km, right? So when M is large, then the rate climbing up almost 1. Now, there is a paper, very technical, but it's an excellent work, that says your M, your extension here, should not be too high. Because if you're too high and your rate goes beyond 0.87, then the structure of that code is actually less random. Less random. So that it's no longer indistinguishable from random code. It becomes, somebody can say that's COPA. And I can find G. And I can guess the L. So that's not good. That's why there is also a cap on how big this can be. So this paper is essentially saying you can bring your M, but not too high. If it is too high, it will go beyond that, and there is an attack. Okay, understand? Now, example of current 80-bit security has this parameter. Now the rate is 0.828. It's still below this. It's fine. The minimum distance is at least 65. So it can correct 32 error. Okay, there are lists of recommended parameters in the literature for various security level. But here you need to check it periodically, whether there are new attack or not. So in one sentence, code base is still being investigated. Okay, ongoing. So thank you, and I'm happy to answer questions if you still have some.
What is the comparison between another post-quantum cryptography and it's the same security?
Oh, okay.
The design.
All right. Okay, so the question is, how do you compare the security to other candidates? Actually, very, very good. Yeah. So, what happened? Okay. All right. So here is the full report. Oh, sorry. I haven't stopped sharing that. I should share something else. I don't remember exactly what's the number, the comparison and all, but it's here in this report I mentioned earlier. Okay. So here in the report, it says what we are selecting, okay, the crystal Kuiper and all that. This actually is a very interesting report if you want. Now, here it explains how NIST or this general standardization process look at the comparison. Okay. Perfect correctness, which is very nice. Yeah. Security. Okay, so here it tells you what are the it says all of those attacks are actually very costly. Okay, oh, sorry. Okay, so in general, it says, while algebraic techniques have been used to break variants of mechanisms based on other algebraic codes or based on Gopa codes with additional structure, this technique is costly than information set decoding for attacking classic mechanisms. So all those attacks that breaks other systems is more expensive to implement than a straightforward attack on this. So in this language, actually, if you want to summarize it, we have strong confidence on the security of this, even more on any of the other code-based crypto systems. But here, the problem, very large public key size and slow key generations. This makes it undesirable in many common settings. Okay, so here, in settings where a public key is reused many times and does not need to be retransmitted, it is possible that the performance profile could have some advantage. Meaning, if you are creating a public communication channel and you're protecting this within using a key which is protected by mechanism, and this link is persistent, so it's not like every time you need to connect, you need to build a new tunnel, then it may make sense. Because although it is expensive to generate, the key is large, but if you need to transmit the key once and then you use it for a long time, then it makes sense. As I mentioned to you, some agencies, some type of military unit may prefer this. In fact, the German cryptographic agency, so the BSSN of Germany, they say that for some purposes use mechanism, specifically use mechanism. So in terms of security, it's very strong confidence in the mechanism crypto system. Because among most of the proposal for post-quantum, it's the oldest. It has been attacked relentlessly for many years. Very sophisticated attack. Nothing happened. So when we are comparing the strength, that's a rather hard thing to do, because again, the calibration is based on the confidence of, do we have confidence on this crypto system? And it's not like, okay, so if you use mechanism of this dimension of this length, this is equivalent to crystal Kuiper of that parameter. That's very hard to make. However, we do have a basic standard. For example, if you look at the NIST document that calls for this proposal, I forgot the detail, but they have five level of security. So level 1 is this, level 2 is this, level 3, level 4, level 5. So it must satisfy this and that. I think mechanism is between 4 and 5. So it's super strong. Again, here. Okay. I hope that partially answered.
As we know, there is many approach to post-quantum cryptography, but why there is no multivariate approach on the NIST?
Okay. The question goes like, okay, why is it that the scene is dominated by lattice-based and code-based? Why not multivariate and the others? There are many possible explanations to it. One, multivariate is something new. Code has been studied for a long time. Lattice for hundreds of years after. Lattices started with the question in algebraic number theory, way in the 18th century, and code-based also benefit. But multilinear as cryptographic tools are new. So not many people know or have a feeling of how to build and how to design crypto system from that. It doesn't mean that it's not good. It might mean just that we are not yet used to it. The community may not be used to it. The second part is, this is my answer, which is not, I'm not an expert in multivariate. But if you look at the structure from linear algebraic perspective, it looks like it's complex. Because code base is straightforward linear algebra. But if you have multivariate, it's no longer a single variate like this. Like Bapak code is single variate, it's already look complicated, right? Now, if you want multivariate, okay, so you have Z1 and Z2 and Z3 and Zn. So I can imagine from a perspective of algebra, this will kick up the problem to a higher level of complexity. It doesn't mean that it's not good. So those are, I think, it's an explanation I can offer.
So I think that's it. Because then we can end this session.
Thank you.